Hello, this is group number one. We'll be introducing on topic number two, the icing model for an AV alloy system using kinetic Monte Carlo technique. Each of us will introduce one topic of the presentation. As such, we introduce each other as we go. First, I'll touch on the background. On the right, the equation for energy calculation of the spin interactions can be seen. This equation is a good approximation, but not completely realistic model, which we will touch on later. For now, let's continue. It takes into account the distance between the spins, as the separation plays a role into the electrostatic interactions, which is counted for in the equation. However, we tend to restrict the system to the nearest neighbors. This is realistic because the electrostatic effects are very short range, and this is the icing model. On the bottom, we just can see a demonstration of the spin alignment as the energy gets lower. What does this mean? This is known as the Pauli exclusion principle, and it demonstrates how the spins go from completely randomization up down, which is white and black, towards a more complete same direction spin. Next, I'll be talking about its applications. Since the model it's very used for its ability to represent random exchange interactions, it has a wide number of applications, one of which is the melting of a heteropolymer, which uses the icing model coupled with a Monte Carlo technique, which we will touch on later, to acquire time-dependent correlation functions. It also uses it is used in combination with atomistic resolution models to demonstrate through simulations the coarse graining approximation theory. Some of its most common applications have been to test 2D and 3D classical nucleation theory, which further goes into demonstrating the importance of temperature dependence in surface energy calculations. It even has been used as a form of symptom-to-symptom association in psychological studies by being represented as a pairwise interaction between binary variables. On your left, you can see two diagrams. These are just representation of some data acquired in icing models. It is just the nucleation rate calculated by FFS for a 2D and 3D icing model. I hope I have shown you its various applications and how the icing model is important. Now, Neil will talk more about the implementation of the physics and techniques to further develop on the icing model.
Hey Professor, this is Neil and I'm going to be explaining the theoretical aspect of this project. So first I want to explain the Metropolis Monte Carlo method for the icing model. The flowchart on the right actually shows the algorithm quite clearly, but just to walk through it, first we'll get an initial configuration of n spins, then we'll choose randomly one of the points and flip its spin. Then the change in energy because of the flipping is calculated, and if the change is less the move is directly accepted, and if the change is greater then the Boltzmann probability condition is used to accept or reject that move, and steps 2 to 4 are basically repeated one after the other. Now I'm explaining the Metropolis method because this actually gave us a decent idea on how to proceed along with the coding. Now this method is only for flipping the spins, but the program that we did actually has atom exchange as well as flipping the spins. So it is main algorithm is a little different, but the theoretical foundation was sort of this algorithm because after doing assignment 6 after assignment 5 it gave us a better understanding on how to deal with kinetic Monte Carlo. So now I'll be explaining the mean field approximation theory. So for solving the Ising model, we need to do some approximations. It's the mean field theory is basically the first recourse that is always used to construct a theory. So there are many different theories that are used, but we'll be using the Weiss mean field theory. Now the first equation here signifies the Ising configurational energy. And here the Sj, Sk are the spins, J is the coupling energy, and H is the applied magnetic field. The second equation basically gives you an approximated value where the value of HMF is given as a sum of H and JZM. J is the coupling energy, and M here is the magnetization per spin of the lattice points. Now, the magnetization per spin is nothing but the summation of all the spins over the total number of spins given, or the total number of particles. So the third equation is basically the single spin Boltzmann distribution to predict the value of magnetization. Now, the mean field approximation is actually used to replaces the configurational energy by the energy of a non-interacting system of spins, each which are experiencing an applied field HMF that is given here. And the fourth equation basically is sort of a consistency fulfilling equation. So to keep the consistency, the value of M, which is predicted by the Boltzmann distribution, must be equal to the value of M, which will be used in the HMF equation. And therefore, by substituting equations and doing some cosmetic changes, we get the value of M as tan H of beta HMF. So, lastly, I will be explaining the analytical steps for solving the Ising model. Now, I know that we are solving the model by kinetic Monte Carlo, but the computational method actually it does not really help that much with the physical understanding of the model, and therefore we also wanted to study how analytically the model was solved. So now we know that in the model we take that it's of canonical ensemble where the probability of each microstate is e raised to minus beta e by z. The first step in solving the Ising model is basically just writing the Hamiltonian as a sum over the bonds for the configuration. Then we'll be focusing on a particular bond and we'll be writing down the transfer matrix. Now, it is actually seen that the summation over sigma j, it is similar to, actually, it rather is matrix multiplication. Then we will be rewriting Z as the trace of a bunch of transfer matrices multiplied together. So a transfer matrix is just basically a notational trick that is used to describe Z, the partition function, much more effectively. So similarly, we'll get the average spin and the correlation function. And lastly, we'll be diagonalizing the matrix and then explicitly calculating these quantities. And for that, we need to find the eigenvalues and eigenvectors of these transform matrices. So even though I really casually explained these steps from reading about the 2D analytical solution, at least I tried to read through it. I understood that the mathematics and the complexity of the problem is actually quite hard to determine.
Hi Professor, I'm Shin and I'm in charge of the result analysis and the theoretical part. We mainly have two results, the preliminary result and the modified result. For the preliminary result, we separate the Lennard-Jones potential and the spin energy. For modified result, we combine them together. I will briefly talk about our case. We are going to discuss the IC model for AB alloy. In our system, there is binary A and B, binary spin up and down. For the preliminary result, we assume that the spin configuration is independent of the atom configuration. The energy barrier of B is twice larger than the barrier of A. We use Lennard-Jones potential to calculate the system energy and Ising model equation to calculate the spin energy. We use the Bragg-Williams theory to calculate the average spin, which is the difference of plus and minus divided total. For the preliminary result, we first build up a 10 times 10 FCC lattice, as 50 times 50 takes too much time. Initially, we have a random alloy and random spin, as we assume that the spin energy has no influence on the diffusion process. We first calculate the lattice energy using Lennard-Jones potential and use KMC to get the diffusion. Then we calculate the spin energy and using Ising model and use KMC to get the spin flip. From this figure, we can clearly see that the AB alloy tend to segregate at low temperature. Also, the spin tends to align at low temperature to minimum the system energy. As the temperature is low, the energy is easily to achieve the convergence. At high temperature, the AB alloy will tend to be disordered as they get enough energy at high T. Besides, the spin also tends to be disordered. As the temperature is high, it's hard to achieve convergence. From this spin figure, we consider that there will be a transition temperature for spin of AB alloy. This time, we keep the B concentration at 0.1 and change the temperature of the system. From this figure, we can see that there is a clear transition temperature for average spin changing. However, there is some problems of our assumption. First of all, the spin energy also influences the diffusion process, and we cannot separate them. In other words, when we calculate the diffusion process, we need to consider the total energy, Lennard-Jones potential, and spin energy. Besides, the value of J also has an effect on the system, and we consider to use a real system as we can compare the altitudes of Lennard-Jones potential and spin energy. Later, my teammate Lee will introduce the code for iron-nickel system.
Hi, Professor, this is Lee. So, to investigate the evolution of spin and atom configuration in our iron-nickel system, our group first did some research about basic parameters used in Lennard-Jones potential model and Ising model, which you can see in the tables. It needs to be pointed out that as J is unitless in most literature, we add unit electron volts and change the value to make constant J more applicable to the simulation. In the following sections, I will go over the code in detail. At the beginning, we define two functions which are used to calculate potential and magnetic energy. In Lennard-Jones calculation, we indicate iron S1 and nickel S2 for the convenience of coding. It might be confusing if you look into lines about comparing what kind of particles the specified atom and its adjacent are. We will discuss that in the following slides. We utilize lengths as 2 to 1/6 while the potential energy reaches its minimum. When it comes to magnetic energy, we set the spin +1 and -1 for different situations. In this section of lattice and neighbor list construction, we want to generate lists containing every atom's position and its neighbors. And the index of these lists are also related to the atoms we want to investigate. In 10 times 10 lattice, we have 200 particles. If you want to find information like its position, neighbors, the spin and property of particles 40, for instance, you can easily find it by searching those lists with index 39. This rule also applies to spin and alloy lists. In this part, we first created a list to arbitrarily generate alloy based on concentration of nickel. We denoted iron as 1 and nickel as 0 in this alloy list. And then we built a spin list where spin plus 1 and minus 1 share same probability, 50%. After the basic settings ready, we first calculated the total energy, the combination of potential and magnetic energy for the convergence criteria used. In the main loop, the simulation starts with generating a swap list by making use of neighbor list. If adjacent atoms are of different kinds, the index will be added to the list. When the work is done, the total energy calculation of particles which may switch their position begins. This simulation will compute the energy difference before and after the swap. If the add switch is preferred, meaning that the final energy is less than the initial one, the switch rate will be calculated only by making use of the migration energy, and if the switch is not preferred, that additional energy barrier will be added to the Boltzmann factor. After the rate of all possible switch is collected, which pair will be lucky to make that switch will be determined by the traditional kinetic Monte Carlo method. The process of spin flip is similar to the atom exchange section. The difference is that the chance to make that flip is considered individually, and along with our previous model, we decide that the flip energy barrier of iron is half of that of nickel. In one iteration, when both atom exchange and spin flipped are decided, we implement the above convergence criteria to see if the simulation is worth continuing. When the total iteration is larger than 1000 steps, the simulation will check if the energy at that step is the same as 1000 steps before. If yes, the loop will break. Also, in case some unexpected situation happen, like the running time is massively long and the energy expands severely during fluctuation, we added another two criteria to make the code run smoothly. So my part about codes and convergence criteria is over. Let's go back to Xin and he will further talk about our results.
For 2D icing model, there is already the analytical solution to solve it. Therefore, from this literature, we get the expression for energy per spin and the average spin. Besides, from the expression, we find a relation between transition temperature and J value. K times Tc equals 2.269 times J. For iron-nickel system, if J is 0.15 electron volts, the transition temperature should be around 3900 K. Once we get our theoretical temperature, we try to use our model to test it. Here is our main result for the modified model. For the above two figures, it's a diffusion process for iron-nickel system. At low temperature, there's no diffusion. However, the atom changes the spin to achieve minimum energy. Therefore, the average spin is larger as the spin tend to align. From this result, we can see that the activation barrier of changing spin is smaller than that of diffusion. Also, it's very easy to achieve convergence criteria at low temperature. This time, we change the temperature to 3900 K. We see that the atoms start to diffuse as they have enough energy. As the temperature is too high, they will tend to be disordered rather than segregate. Besides, the spin tends to be disordered, which means that there is a transition temperature of spin changing. From the right two figures, we can guess that it's hard to achieve convergence at high temperature. For the results, we found that the transition temperature is 3500 K with nickel concentration equals 0.5, which near the theoretical result 3900 K. By comparison, it shows that our model works well, and we also found that different nickel concentration also influence the transition temperature. For smaller concentration of nickel, the smaller transition temperature, which means it's more easy to change spin with low concentration of nickel, as nickel has larger activation energy barrier than iron. We can also explain this from the theoretical model. When we calculate the transition temperature, we use the nickel-iron interaction J. Therefore, 0.5 concentration should be similar to the transition temperature, as there are a lot of iron-nickel interaction. However, with smaller concentration of nickel or larger concentration of nickel, as there will be more iron-iron interaction or nickel-nickel interaction, it will have a smaller transition temperature. This is mainly because the J for iron and nickel-nickel is much smaller than that for iron-nickel.
So this is actually the resulting plot of temperature versus magnetism per spin versus the concentration that we got from using our model. So for data collection purposes, we actually stopped running all the simulations at 10,000 steps as the time required to run the program was very high. So initially we observed that most of the simulations were accepting our convergence criterion and stopping before 10,000, but later on there were also many simulations which actually had to be stopped at 10,000 and they hadn't reached the convergence criterion yet. This is basically the main reason that we think the results are inaccurate because the system hadn't really reached or hadn't satisfied our convergence criterion yet. So we can see that the magnetism per spin hasn't gone to complete zero, but it is decreasing with temperature, and this decrease with temperature of the magnetism uh, shows that the general trend of the results is basically correct because at a low temperature we can see that the magnetization per spin is rather high, it's about 0.65, and while at higher temperature it goes down to about zero point 0.2. So the temperature range is varied from 500 to 5000. The concentration is varied from 0 to 0.85. That is the concentration of the B or the nickel atom in the FeNi or AB system, and the magnetization will always be between 0 to 1. The magnetization per spin dependence on the concentration is mainly because of the coupling energy between them. So for this system, actually, we had reduced the value of the coupling energy than what we got from the literature because the values in the literature were too high and the system behaved a little unstably. And therefore, we can see that not much effect is seen with change in concentration. The major effect is only seen with change in temperature. So basically, this is the temperature versus magnetization per spin versus concentration graph that we got as a result.
In conclusion, increasing spin energy makes atoms hard to diffuse. Increasing temperature makes atoms have a longer time to achieve equilibrium. Increasing nickel concentration leads to a higher transition temperature, and they will approach a theoretical temperature, which can be calculated by the equation. Increasing temperature makes this system hard to achieve energy convergence. At low temperature, the spin flips while there is no atom diffusion. This is mainly because the spin energy is smaller than the Lagrange's potential. Therefore, if the Lagrange's potential is smaller than the spin energy barrier, the atom tends to diffuse at no spin flip at low temperature.